Good evening, everybody. Good evening. Now 6 o'clock, so I think we should make a start. I'd like to welcome everybody here to this, the 30th meeting of the AI Civic Group for National Arts and Manchester Statistical Society. Great to see so many people here. Our speaker this evening is Dr. David Hoyle. Some of you will know David. He's a member of the Society. He also spoke and he addressed the AI City Group about 18 months ago.
Yeah, just the madness that can go like wondering if it's a shirt.
He started off at the University of Bristol. He studied for a BSc in mathematics and physics. He then took a PhD in theoretical physics. Since then, he's had a very varied career in both academic and commercial sector at the universities of Manchester, Cambridge, Exeter, and also in the commercial world at Lloyds Bank, Humvee, and Auto Trader, among other businesses. Since 2020, he's been the research data science specialist at Humvee, building demand forecasting models and algorithms for the grocery sector. He's also the chair of the local Manchester branch of the Royal Statistical Society, which I believe is an organisation nearly as old, almost. So please welcome David, who is going to speak on the mathematics of transformers and large language models. David.
So, thank you. Yes, my name's David Hoyle, and I'm going to be talking about the mathematics of transformers and large language models. This is very much an introductory level talk. It's a technical talk, but it's intended to be ease you into some of the mathematical details that are inside some of the tools that you might have used already, like things like ChatGPT or Claude. It's actually, as I say, an introductory level talk. So for some of you who've already got some familiarity with the technical details of large language models, you may or may not learn something new. I hope you will. It's actually a talk I gave as part of a presentation, a 2-hour bootcamp tutorial session at the Open Data Science AI conference that I gave a couple of months ago. There I had 2 hours to go through the material. Now I've got a bit less, maybe about 50 minutes. So I have had to actually cut down some of the content, take a lot of it out. But rather than think of it as, you thinking it as maybe you're getting the cheap version of the talk, think of it as you're getting the bespoke version of the talk. Okay, but because of that more limited time, I'm not going to give you a marketing and sales pitch about me, particularly since Philip's just done such a wonderful introduction. If you do want to know some details about me, there are some details. You can also go to my LinkedIn page. Right. What am I actually going to talk about? Well, I'm actually going to start off very gentle and then ramp up. So I'm actually going to start off with the learning objectives. What do we aim to get out of this talk? What do we want to achieve with this talk? Then I'll move on to our main goal, which is actually predicting the next word in a sentence. And I'll explain to you why that is actually quite a powerful capability and why being able to do that leads to some of the powerful tools such as ChatGPT and Claude that you may already be using. And when I'm trying to do that prediction of the next word, I'm going to start by trying a very simple and naive approach. And that approach will be wrong, very deliberately wrong, because learning how it is wrong will actually indicate to us what we actually need in a more realistic system. And that will bring us on to things like word embeddings and transformers. And then once I've delved into the mathematics of what's inside a transformer, things like self-attention, multi-headed self-attention, we will come back to our main goal, predicting the next word in a sentence. And then finally, we've got time to wrap up. Right, okay, so what are we going to learn in this talk? As I said, we're going to go into the mathematics inside transformers, which are part of large language models. So we're going into the mathematics of what's inside a large language model. We're going to cover those mathematical details largely at a high level. We're talking about concepts. There will be some equations in there, but I hope to unpack those equations for you and explain them in English language. So there will be some equations. Don't worry if you don't understand them. I often forget them. What I'm going to try and do is actually explain them to you in a bit more of a common sense type of way. If I've achieved my aim, then by the end of the talk, you hopefully will have lost some of your fear of what's actually inside the science inside those LLMs. So that's ultimately my end goal. What we will not learn is how to actually train those large language models, okay? So I'm not going to go into any of the details of how we train foundational models. You're not going to build any chatbots in this session. I'm not going to teach you how to prompt. I'm only going to mention agentic AI in one place. And I'm afraid by attending this talk, you're not going to turn into AI billionaires and not even trillionaires, I'm afraid. So none of you are going to be competing with Elon Musk today, I'm afraid. Right. But I am going to assume you do know something already, a bit about data science. Maybe you've got some basic familiarity with basic linear algebra. I'm hoping you know what a matrix is and that matrix multiplication represents a linear transformation. I'm also going to assume that you are familiar with something about training of machine learning models. Specifically, I need you to be familiar with the idea that we get parameters in a model by minimizing some loss function on historical training data. And the reason I need you to understand that is throughout this talk, I'm going to be referring to parameters in these transformer models. And there's going to be a lot of these parameters, believe me. And I'm going to be referring to these parameters. And all I'm going to say is we can get values for these parameters by training on some historical data through a training process. I'm not actually going to go into the details of what that training process consists of. We haven't got time. So I need you to be comfortable with the idea that if I refer to some parameters in a model, that we can get values for them, and it's a sort of, it occurs via some reasonable process that maybe you've done before, maybe you haven't, but at least you're not viewing it completely as magic. Right, okay, so let's move on to our main task, predicting the next word. And I'll also explain why that is actually a very useful capability, why it enables the sort of powerful tools such as ChatGPT and Claude. But let's actually start really simple. I've got that familiar English phrase that a lot of people use when explaining things like natural language processing. The cat sat on, and hopefully everyone in this audience will go, right, the obvious next word is the. Okay, so if you've said the, great, give yourself a pat on the back. What we've been able to do there is predict the next word. We started with that short partial sentence, that short prompt, if you like, that short bit of context, and that gave us information enough to actually predict that the next word should be the. What we can then do is take that word the, we can tack it on the end of that short partial sentence, and that gives us a new short partial sentence, and we can just repeat this process. So we can build up the sentence even further. So if we repeat the process, we've now got the next bit, the cat sat on the, and hopefully you all go, Matt is the next word. So what we've been able to do there is take that very short partial word, that prompt, the cat sat on, and extend it by 2 words, okay? I could have continued that process a bit further. Maybe I could have taken a different partial sentence and used an AI system to extend it actually into a full paragraph. Or maybe I could have taken a whole paragraph and used an AI system to actually extend it into a whole short story, okay? For me, that's actually quite a powerful capability, but you may be looking at that and going, actually, how useful is that? Unless you actually want to write a novel or short stories, maybe that isn't actually that useful. You might be saying, how does the ability to actually write short stories lead to these powerful capabilities that you see coming out of ChatGPT and Claude and other large language models. Okay, the thing is, we need to realize that words are the natural units of sentences. We can break a sentence down into these natural units. We call these natural units tokens. So the goal that we're actually trying to do is not so much next word prediction, it's actually next token prediction. Our goal of what we're trying to achieve is, can we predict the next token given the preceding sequence of tokens? Now, when we look at a sentence, when we break it down, there are other ways in which we can break down a sentence into tokens. There are other tokenization schemes. And typically in a modern LLM, they will actually use one of these more sophisticated tokenization schemes. I'm not going to go into any of the details around these more sophisticated methods. I'm just going to stick with breaking my sentence down into words. So I'm always going to view my tokens when I'm talking about language as being words, just because that simplifies the explanation I've got. But you should realize what we've got here is predicting the next word is an example of being able to predict the next token. And being able to predict the next token is extremely powerful because sequences of tokens are absolutely everywhere in the world. Take something like a movie. A movie is a series of individual units, in this case, images. Images themselves are sequences of pixels. So you can think of the actual individual unit or tokens in an image as being the pixels. When we move into the scientific domain, so something like molecular biology, take a DNA sequence. It's a sequence of bases. A protein is a sequence of amino acids. So the tokens in that case are the amino acids. When we move into, say, the business domain, you can view a business task or a business process as being a sequence of individual decisions and a sequence of individual actions. So now that's when we begin to realize that being able to predict the next token in a sequence of tokens allows us to do things like task completion. By being able to predict what is the best next set of decisions, the next best set of actions to take, we're starting to move into the realm of agentic AI. So, although for the rest of this talk, I'm going to be talking about how we predict the next word in a sentence, what I want you to sort of get is that is just an example of predicting the next token in a sequence of tokens, and next token prediction can be a very powerful capability. Right. Let's take our task of next word prediction and let's try a very simple, naive approach. So I've got my starting sentence again. The cat sat on the mat. Now, if I were modeling just that sentence, you'll see in that sentence there are 5 distinct words. So I've got a vocabulary of just size 5. And I can represent each of those words using a 5-dimensional vector. So, for example, I could represent the word cat using the vector 0, 1, 0, 0, 0. And the 1 there is essentially telling me that cat is the second word in my vocabulary. Okay, so I've got a very simple way of numerically representing the words in my vocabulary. But actually what I really care about, what I want to be able to do, is I want to be able to represent the prompt, the actual partial sentence, not the individual words. What I want to do is be able to represent that numerically, because essentially that's what I want to take into account when I'm predicting the next word that would follow on at the end. So how am I going to represent that numerically? I could take a very naive approach. I could just say, right, let's take those 5 words and let's just combine the vectors that represent each of the individual words. Let's combine them into some sort of, in this case, a table or a matrix. So in each column, I've got its representation, its individual vector, and there's my prompt, represented numerically. But you can look at that and you'll soon realize, well, actually, there's lots of ways I could have filled in that potentially table, lots of ways in which I could have rearranged the 0s and 1s. In fact, potentially I end up with 5 to the 5 different potential combinations for my input prompt. So I'm talking about an input prompt space that is now 3,125 dimensional. So although I started with a very small vocabulary, I've now got this massive input prompt space simply because I was naive enough to represent my prompts by combining the vectors in a combinatorial way. Now, you may have spotted or begun to spot what the issue with this is that when we move on to a real language, that problem only increases. So the English language, typically, you've got between about 170,000 and 700,000 words, depending on which dictionary you consult or use. When I Googled that, I got a range of different numbers for how many words in the English language. I was a bit surprised it was that wide, but you know, lower bound number 170,000, upper bound maybe 700,000. So that's a huge vocabulary size. If I start to represent my words using vectors in the same way that I did before, using that sort of one-hot encoding, my vectors are going to be very, 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 very long. Okay, and if I then also try the approach I did on the previous slide for representing the prompt by combining vectors, I'm going to get input prompt spaces and input prompts that are absolutely massive, got huge dimensionality, way beyond the size of any LLM. And LLMs already are known for their massive parameter size. So this naive way of actually representing the prompt just isn't going to work when I've got vocabulary sizes that high. So I need to solve two problems here. First of all, I need to reduce the dimensionality. I need to represent my words, my individual tokens, using much, much smaller vectors. Secondly, I need to use vectors to represent the words that somehow also incorporate the preceding context, because I can't represent that context, that prompt, by combining the vectors. I need that context already to be inside the vectors that I'm going to use. So somehow I need to not only use the vectors to represent the individual words, but also represent the context that went before them as well. They need to be aware of the context. In other words, I need to create context-aware vectors. Right, so I've got two problems to solve. Let's tackle the first one. How do we reduce the dimensionality? That brings us onto the topic of word embeddings. So what is a word embedding? Well, let's go back to our simple example again. I had these 5 words. I could represent them by 5-dimensional vectors. I had 5 words, so I've got 5 data points. Those 5 data points live in a 5-dimensional space. But I could map those 5 data points down into a 3-dimensional space, okay? I would still have 5 data points, but they now just sit inside a 3-dimensional space, a cube, if you like. And because we're taking the original data points of 5-dimensional vectors and we're mapping them down to inside that 3-dimensional space, we say we're embedding those data points inside that 3-dimensional space, hence the word embeddings. We're creating embedding vectors in this smaller space, okay? Now, we could possibly do this, create this mapping process via using, say, a neural network autoencoder approach. And that would mean taking these points in the 3-dimensional space and seeing if we can predict and use them to predict the original words. If I've got a good mapping, the data points in this 3-dimensional space will very easily lead to the prediction of the original words, okay? So I will have a low reconstruction error. So this gives me a means of actually working out how to create this optimal mapping. What I can do is take something like a neural network, train it until I've reduced the reconstruction error to be as small as possible, and then I've got points in this 3-dimensional space that allow me to have very good representations of the original words. Okay, so that's how we might create that mapping. When it comes to real LLMs, we just follow exactly the same process. Okay. It's just that we have much bigger vocabularies, we have much bigger training sets, and we also map down to much bigger dimensionalities. So instead of mapping down to, say, a 3-dimensional space, we map down to something like maybe a 300-dimensional space. Modern LLMs, when they work on the English language, they don't actually tend to use all of the English language. They might use something like a vocabulary of 30 to 50,000 words. And one of the original early pieces of work in this field of word embeddings, one of the original pieces of work, this system called Word2Vec, mapped those English words down into a 300-dimensional system. Now, you may be looking at that and thinking 300 dimensions is still very, very big. But actually what you should be comparing it to is the size of the starting vocabulary. It's a massive reduction on that starting vocabulary size. It's still big enough that we can actually capture a lot of the meaning of the words and the semantics. So 300 dimensions allows us to capture a lot of the richness in the English language, but it's a huge reduction on what we started with. Modern LLMs, again, they map down to slightly larger dimensionalities, but still a lot smaller than the original starting vocabulary size. For a modern LLM, we could just use the mappings. We could create the mappings via some separate training process, or we could maybe use off-the-shelf word embedding processes. So, for example, we could just take the word-to-vec embedding vectors that are out there and they're in the public domain. More typically, what happens in an LLM is that mapping process is actually considered to be part of the model. It's just a setup. Like I said, it could be via a neural network. That neural network has parameters. Those parameters are considered part of the overall large language model, and we just learn that mapping process via the training of the large language model. But other than that, the principle is exactly the same. Right, okay, so here's some examples of some actual word embeddings. As I said, the word to vec work was done about over a decade ago, about 14 years ago, I think. Yeah, 14 years ago. And these vectors, for example, here's some vectors. They were actually created by training on Wikipedia articles. These vectors are actually freely available. They're in various programming language packages. So I just went to the gensim package in Python, looked them up for my various words, and I've just listed them here. And as you can see, they're just numeric numbers. You know, they're just representation. They're just a vector. It's a numeric representation of that word. I've got the words in my sentence across the top, and you can see the vector for the word the here is exactly the same as the vector for the word the here, because it's the same word, as you would expect. Okay, right, so we've solved our first task. We managed to reduce the dimensionality of the vectors that we use to represent these tokens, these words, but have we actually managed to solve our second task? Our second task, just to remind you, was how do we actually represent the preceding prompt? How can we do that numerically in an efficient way? Can we use vectors that not only represent the words, but take into account the preceding context? Okay, well, let's have a look. Imagine if I actually tried to predict the next word. Here's my partial sentence. The cat sat on the, and I'm wanting to predict the next word. Obviously, the next word will be Matt. But here in these columns, what I've got is are the word embedding vectors that I might have created earlier. So, for example, in these actual cells here, I might have the numbers that you saw in that previous slide, that previous table. I've actually highlighted in a slightly darker color the embedding vector for the last word in this prompt. And the reason being is, ideally, I'd like to use just this vector to predict what the next word is going to be. The reason I'd like to be able to do that is that's actually a relatively simple machine learning task. It's machine learning 101. It's taking a vector of features to predict a label, predict a sort of which class I'm in out of a large vocabulary. And so it's the kind of thing that you learn when you're sort of doing a first year class in machine learning or data science. Given a training data set, I could train a multi-class classifier to predict what the next word is, given that input set of features. The only problem I've got is this vector here actually knows nothing about the other context in the other words in my prompt. So this vector here knows nothing about these words here. So it's probably not actually a very good word for predicting the next word. Okay, so you all managed to predict that the next word after this short sentence was Matt because you were able to read the whole sentence. If all you knew was the word the, you may not be able to predict that the next word, the following word should be Matt. So just this vector on its own is probably not is not going to be that helpful. Somehow we actually need to create new vectors for each of these words that not only represent the words, but also take account of the preceding context. They have the information about the preceding words baked into them. If we can do that, then we stand more chance of being able to predict what the next word is going to be, just on the just given a single vector. So somehow we need to take these vectors and we need to transform them. That's what we do with a transformer. That's all a transformer, the main guts inside a large language model, is. It takes an input embedding vector and creates a new vector that not only represents the word, but also takes into account the preceding words that are in the prompt. Okay, I'm going to shift the goalpost slightly for the purposes of explanation. For the next couple of slides, I'm going to actually show you how we can use a transformer to create new vectors that actually take into account the whole context of the sentence. So when, for example, I'm trying to create a new vector for this word "the," I'm not only going to try and take into account the preceding context, I'm also going to take into account the words that follow on afterwards, i.e. the word "mat." Now, you may be looking at that and go, isn't that cheating? If you're going to use the word "mat" to construct a vector here that you're then going to use to predict the word "mat," it looks like you're cheating. It is a bit, but it makes my my task of explanation slightly simpler. What I am going to do is I'm going to come back later and show you how I can just use the preceding context. So for now, I'm going to take a slight detour just to make my explanation slightly simpler. So what are we trying to do? We're going to try and start with taking these original columns, which are my vectors, and we're going to try and update them to create these pink columns. These pink columns represent each word. For example, this column here will represent the word "the," but it will also do it in such a way that we take into account the preceding words that went on before it, and also the words that have gone on the other side. So how might we do that? How might we actually create a word, a new vector that somehow takes into account the information that's going on around it? Well, the most obvious thing to do is, why don't we just take a weighted average of those different vectors? So if the columns are my vectors y, I'm going to create a new vector, my output vector, as just some sort of weighted average of my starting vectors. So here's my vectors. Y, and I've just got some weighted average. The symbol there, A and N dashed, is just a weight. It's a probability. And it tells me how much weight or how much probability should I assign to token N dashed when constructing the new vector for token N. Okay. In other language, you can think of this as how much attention should I apply, should I pay to token N dashed when creating the new vector for token N. So we call these attention weights, hence the symbol A, and hence why the whole mechanism is called attention. These numbers here tell me how much attention I should pay to the other words in the preceding or surrounding context when creating my new vector. Right. At this point, you may be going, well, okay, I get that idea, take a weighted average, but are the vectors y the best vectors to take an average of? Are there maybe some other vectors I can actually take an average of? Is there something else I could do? Well, yeah, maybe there is, but ultimately I still want the vectors that I'm taking an average of to be essentially related to these starting input vectors. So whilst I might consider taking an average of some different vectors, I still want them to be related to these blue columns here. So somehow I want them to be a simple transformation of these starting input vectors. How could I transform my starting input vectors before I take a weighted average of them? What's the simplest thing I could do? Well, simplest transformation I can use is just a linear transformation. So that's what I'm going to do. I'm going to take my starting vectors. I'm going to take a linear transformation of them. This gives me some new vectors v, and it's actually the v vectors that I actually take a weighted average of. Okay. My linear transformation is just represented by a matrix. I just view that matrix as some parameters in my model. I learn it through a whole training process. So again, this is where I was saying I want you to be comfortable with the idea that a matrix represents a linear transformation. All I'm doing is taking my original columns, transforming them linearly to get some new vectors, and I just take a weighted average. Great. So this tells me how I construct these pink columns. But you're probably asking, well, where do we actually get these numbers from? Where do we actually get the attention weights from? Right, well, there's two things we need the attention weights to take into account. So first of all, we want the attention weight for n and n dash to depend upon the starting vectors for tokens n and n dashed. We probably also need those attention weights to depend upon the similarity between the two vectors that represent those words. And I'll try and convince you of that. Imagine I'm trying to create a new vector to represent the word the. Not only do I want it to represent the word the, but I also want it to take into account the preceding prompt, the preceding context. In my preceding prompt, I might have had another instance of the word the. That preceding instance of the word the should actually be a very good signal for how to represent my later instance of the word the. So in other words, I'd want my attention mechanism to put a very high weight on the earlier instance of the word the. So whenever I have very similar words or very similar tokens, I want to have a high weight. Right, so how do we mathematically represent similarity? We use the inner product or the scalar product or the dot product, depending on what you want to call it. In other words, we just calculate the dot product between our starting vectors, and that gives us the similarity between, that gives us a similarity measure, and essentially that's what we can use as our attention weight. Now, some of you might have already spotted there's a problem with that. Similarity, the inner product like this can actually be negative, and you can't have a negative number for a probability, for an attention weight. So what do? We actually use the age-old trick that we use in computer science or data science. Whenever we've got something which we want to be a probability that isn't, we just exponentiate it and divide through by the sum. In other words, instead of using the similarity measure, we just feed that similarity measure into a softmax function. But still, it's a very easy calculation. Once I've calculated these similarity calculations, we just feed it into an exponential. And this numerator here, this denominator here is just a normalization constant. It just makes sure all my probabilities add up to 1. So I've now got a mechanism through which I can actually calculate these attention weights. These attention weights tell me how I should calculate my weighted average. So they tell me how I should average my data to get these new vectors out. But note that these attention weights here, they're computed from the data or the data itself. So we're actually getting our weights for our averaging process, for, to feed into our average calculation. We're getting them from the data itself. So in other words, we're using the data itself to guide how we should process the data. So we call this actually self-attention, because we're using the data itself to tell us which parts of the data we should be paying attention to. Right, okay. Again, you may be actually asking, just like when we were looking at those v vectors, which were the ones we take the weighted average of, are the vectors y, n, and net y, n dash the best vectors to use when we're calculating our similarity measure? Are there some even better vectors that we could actually use? Well, why don't we try the same trick that we did when we created those v vectors? Why don't we see if we can transform these vectors before we take the similarity calculation? So why don't we just apply another linear transformation to them to calculate these z vectors? And it's actually the z vectors that we plug into our similarity calculation, that we plug into our inner product. And that's what we do. Again, a matrix here, U. I'm just going to treat that as another set of model parameters that I have to learn through the whole model training process. You may note that we've actually got 2 instances of the matrix U in this calculation, in this inner product calculation. So we can actually add more flexibility to our calculation if we allow those 2 matrices to actually be slightly different. So I've added a subscript Q on one of them and a subscript K on the other. There is actually a more principled and intuitive reason why I might want 2 matrices here instead of just the single one which I used twice. Why these matrices should be different. It relates to explaining things in terms of query vectors and key vectors, hence why I've got the subscripts Q and K here. I haven't got time to really explain what a query vector is and what a key vector is. So all I'm going to do is say, right, I've just got 2 matrices. I've got 2, they're just parameters in my model. I can learn it through, learn those matrices through the model training process. Right, we're almost there. We're moving along. So our final similarity measure is that formula there. So these were my starting input vectors. These are matrices. I just learned these matrices through training the model. I plug this similarity measure into a softmax function. That gives me my attention weights. I use the attention weights to calculate a weighted average. You may actually see in the literature that formula instead, which looks like it's slightly different. You've got this extra square root factor. At this point, you may be saying, wait a minute, well, are you telling me, David, that the formula you're using is different? Is your formula wrong? Is the research literature right? Which one should we use? They're actually mathematically equivalent. All I do is I absorb that square root factor into the definition of my matrices U. And the reason I do that is it allows me to write my formula in a slightly shorter form. It makes my equations slightly neater, and it means my equations on later slides, well, in other parts of it, look less messy, if you like. So that form and that form are exactly mathematically equivalent. There is a reason why you want to separate out this square root factor, and it actually makes the training slightly more easier to implement, slightly more stable. So there's an engineering reason why we might want to factor it out. Mathematically, it makes no difference. Right, phew, that was a lot of maths. We're almost over all the maths, believe me. So we've got a final formula. This is the formula we're going to use for calculating our new embedding vector that takes into account the preceding context, the preceding part of the prompt. Right, it looks fairly horrible. It's actually a lot easier to understand in English. All that says is we create new vectors to represent token n, the nth word in our little phrase, as a weighted average of these vectors v. The weights we use are a softmax function. This is a standard computer science function that is applied to transformations of our starting input vectors, our starting input embedding vectors. Okay, we just learn these vectors v and the transformation of matrices through the training process. Okay, and that's actually all there is to a transformer mathematically, and that's all there is largely mathematically to a large language model. So if there's one thing I want you to take away, if this is the only thing you take away from this talk, it's that transformers take in input vectors that represent the word, and they output embedding vectors that represent the word, but also take into account the preceding context. That process of calculating the new context-aware embedding vector is just a weighted average. So this scary LLMs, all they're doing is calculating weighted averages. Okay, most of the real scary part in LLMs and things like ChatGPT is actually on how you train the LLMs. It's on the engineering side. The mathematics actually isn't that sophisticated, in my personal opinion. I get scared of the engineering side of things. It's a lot more frightening. Right, okay. I'm going to come back to that little subtlety I mentioned earlier. How do we actually use this approach to actually only use the preceding context? So I said earlier that I was going to shift the goalposts and I was going to take into account all of the surrounding context. How do we actually only use the preceding context? How do we stop cheating? It's actually very easy, because now we know about these things called attention weights. We can easily work out how to filter out the bits of the prompt that we don't actually want to use. We just put 0 in the attention part of the attention weights where we don't want to use them. So for example, if I'm wanting to create a new embedding vector, a context-aware embedding vector for the word cat, I'm allowed to take into account the preceding words, but not the ones which follow on afterwards. So I just assign 0 weight to when I'm calculating the weighted average. That means I filter them out, or in other words, I mask them out. And this whole process is called masking, and so we refer to it as masked self-attention. So we can either put zeros in our attention matrix, our attention weight matrix, or what we can actually do, the other way of doing it is we can just set our similarity measure, our inner product calculation, to -infinity, because then when we feed it into the exponential of -infinity goes to 0. So there's an easy way to do it when we're applying the softmax operation. So I said I would come back and remove that restriction, or I told you I'd shifted the goalposts, and now I'm going to come back. Well, this is how we actually do it. Right, that was an awful lot of maths. So we're now going to move up a level. We're going to make things a bit more abstract. No more equations, or I think there might be a couple, but we're largely going to just actually now sort of explain things in symbols. Let's put all that mathematics inside a box. A bit like a black box, maybe call it a grey box, because we actually know what's inside it. So we're going to actually put all that self-attention, masked self-attention, inside a box, and we're going to call it an attention head. And that's essentially what we're going to use. Our attention head takes an input embedding vector, a representation of the word, and what it does is it transforms it into a new vector, represented by this pink column here. And this new vector not only represents the word, it takes into account the information that was in the preceding words as well. Right. However, there's a bit more sort of detail in how actually transformers actually work, and it's this extra detail that I'm going to go into now. And it all revolves around how we actually use these attention heads and actually how we use multiple of them. And the problem is, when you look at this vector here, when I apply the attention head to it, I'm applying the same attention weights to all the components in that vector. So remember, I've got maybe a 300 dimensional vector. I'm applying the same attention process to the first component as I apply to the last one. Now, it might be that when I'm comparing different tokens, different words, I might consider two words very similar in their first component, but very dissimilar in their last component. This attention head can't actually allow me to do that. It applies the same sort of similarity measures to the first component as it does to the last one. There's no way in which it can say two words are similar in this component, but they're very dissimilar in this one over here. Okay, I can't do it using a single attention head, but there's a very easy solution to that. I just have multiple of these different attention heads. So now I've got multiple attention heads. Each of these attention heads can actually focus and specialize on a particular part of this input vector. So this attention head here might focus on this part of the input vector. This attention head might focus on this part of the vector here. This attention head here outputs a vector here. This one here outputs this vector here. If they output short vectors to get my, say, final long vector, I can just stack them on top of each other. If these output vectors are all of the same length as the output I require, I can just do something like taking an average. So I can easily process the outputs from these attention heads to get my final output embedding vector that I need that is context aware. So, unsurprisingly, this whole process is called multi-headed self-attention. So, we can now begin to see what's going to go into my transformer model. It's a multi-headed self-attention block. But there are further subtleties. That multi-headed self-attention calculation, what it does is it takes the starting input embedding vectors, the vectors that represent the individual words, and it produces these output context-aware embedding vectors, okay? But that attention process, that whole attention process, is column-wise, it's token to token. So when we're actually computing the new vector to represent the word "the," we were working out similarities from this column to this column and this column and so on. In other words, we were doing calculations column-wise. But there may be actually similarities within a single column that we should be taking into account. So although we're using information about how similar this column is to this column, we're ignoring any information about how similar, say, this row is to this row. Okay, so we're missing a trick. We've got potential here to actually improve the whole process even further. What we'd like to be able to do is be able to take a vector and combine the features across the individual components of the vector. We need to be able to take these features and combine them into using some nonlinear transformation to give me some new output vector. If only there were a mechanism by which I could take features in a vector and combine them in a nonlinear way to give me a new vector. Well, there is. I'm a data scientist and I use these techniques all the time because I can just use a neural network. That's what a neural network does. It takes a vector of input features and combines them in a nonlinear way. So all I'm going to do is actually, I'm going to include a neural network in my transformer model as well. Okay, a neural network is just another mathematical transformation. It's got parameters. I've already got lots of parameters, so why not just add a neural network in there as well? I'm adding a neural network in there. I learn what the neural network parameters should be through the overall training process. So my actual transformer block actually now looks something like this. I start with these input embedding vectors that I might have got from, say, something like word2vec. This vector here represents the word the. This one represents the word on. I feed these vectors into the multi-headed attention process. I take the output from the multi-headed attention process, feed it into my neural network, and now I get new vectors. These vectors represent the words, but they also take into account the actual preceding context. And because I've gone through these two stages, these vectors I've got on the right here are highly suitable for predicting the next word. That is my transformer block, okay? We're almost there. By now, you're beginning to be a bit suspicious because I keep on telling you that we're almost there and I keep on introducing extra things. So you're beginning to suspect that I might be lying to you. And you're probably right. What are these gaps here? Okay. There's some extra things we need to add in. Okay. We do actually need to add in a couple of extra things. We need to add in what's called a normalization layer transformation between each of these. We also need to add in an extra combination thing called a residual connection. These are entirely technical stages to the transformer block. They help make the training process easier, more stable, more efficient. Because they are entirely technical, I'm going to not explain anything about them because it's not really relevant to this talk. The thing I want you to focus on, the real concepts inside a transformer block, are this one and this one. So as I say, I'm just going to tell you that they're there, but I'm not going to explain anything about them because it's not really relevant. Right, so, wow, we've got our transformer block. This is what a transformer block looks like. It takes these input embedding vectors and it transforms them into embedding vectors which are more appropriate for predicting the next word. Surely there is no way we can improve upon this. Yeah, you've already guessed it. I just lied to you. Okay. Well, if this transformer block actually takes vectors and gives me even better vectors, there's an obvious way in which I can improve on things. I can take these output in vectors and feed them through another transformer block. In other words, I just stack them all together. And this is what a large language model looks like. It's a combination of transformer blocks. We take our starting embedding vectors, feed them through a series of transformer blocks. Each block has its own neural network, its own multi-headed self-attention process with different parameters. And this is why you end up with so many parameters in a large language model, billions of parameters, because each of these blocks has a huge number of parameters. By the time you've combined multiple of these, you've ended up with an even more parameters, okay? And that's what a transformer model essentially looks like. And we end up with these vectors here. These are context-aware embedding vectors. They represent the word, but they also contain information about the preceding context. They are highly useful for predicting the next word, which means, hooray, we can move back to our original task. How do we actually use those new context-aware embedding vectors to predict the next word? Well, let's try it. So, very similar setup to what I had before. I've got my partial sentence here, my prompt across the top here. But now instead of blue columns, I've got these purple columns. These are my context-aware embedding vectors. Okay. Again, I've highlighted the last embedding vector in a darker color. And it's this vector that I actually want to use to make the predictions of the next word. And it's highly suitable for predicting the next word because by definition, by construction, not only does it represent the word the, it also takes into account all these words that went on beforehand. Okay. So all I need to do is I need to build my multi-class classifier. That's as I said, that's a standard machine learning task. It's the sort of thing you'd learn as part of a data science course or a machine learning course. And we can build a very simple classifier. I'm actually going to use what's known as a softmax classifier. So imagine my vector here is represented by the symbol, the vector f. So what I'm trying to do, I'm trying to build a model that takes that vector f and predicts the probability of each word k in my vocabulary. My vocabulary is very large, so I'm going to get an awful lot of probabilities coming out. And I'm going to just do that very simply using this softmax function. I take my vector f, which is this one here. I combine it with these vectors g, and that gives me essentially up to a normalization constant here. It gives me the probability of the word k, given that I've got this vector, this embedding vector f. Okay, these vectors here in this classifier, again, they're just model parameters. I learn these vectors through the model training process. My whole model has got a huge number of parameters already, so adding in some new extra vectors is hardly going to make a difference. But how do we actually use this in real life? Well, let's go through the process of how we would use that classifier model. So here are my context-aware embedding vectors. This is the one I'm going to use. I feed this vector into my trained multi-class classifier, and it outputs probabilities for me. It outputs the probability of the next word given this is the preceding context-aware vector. You can see the probability for the word sat is actually very low, so that's probably not the next word. The probability for the word mat being the next word is actually very high. It's 0.8. So that would probably be the best word to predict as being the next word in my sentence. So that's what I'm going to do. I predict the word as being mat. And I can just iterate this whole process. I take that word mat, I stick it on the end of my prompt, and I shift my context window along one. So you'll notice I've dropped the word the off the end there, and I've gained this word mat. I look up the starting blue embedding vectors for each of these words. I feed those blue embedding vectors into my transformer model. That gives me new context-aware embedding vectors. I take the last context-aware embedding vector, I feed it into my multi-class classifier. That gives me a new probability distribution, and I just read off which is the most probable word that I'm going to get. In this case, the most probable word is this strange word here called EOS in brackets. It's short for end of sentence. It's basically telling me stop. So now I've been able to use this whole process of using context-aware embedding vectors to actually start with the phrase the cat sat on, and at the end of it I get the cat sat on the mat, full stop, or end of sentence. So we've actually been able to create a solution to our problem. Not quite. One more lie. Yeah, there's one more subtlety I've got to introduce, and that's due to what's called positional encoding. The actual attention weights that we used, they had no information about the positions of the words. And the position of a word in a sentence is highly important. So when you're actually, as speakers of the English language or any language in general, you know that changing the position of a word in a sentence can change its meaning completely. And yet our attention weights don't take that information into account. And I'm going to try and convince you of that. Imagine these are my starting embedding vectors. And here I've got my partial prompt, the cat sat on the. And what I'm going to do is I'm going to rearrange these first three columns. I'm just going to jumble them up. So I've gone from the cat sat on the to sat, cat, the, on, the. So the first three columns have just been rearranged. But the actual attention weight for on sat will actually be unchanged. So when I'm trying to work out the new embedding vector, or I'm trying to calculate the attention weight for how much attention should, when we're calculating the new embedding vector for on, how much attention should we apply to the word sat? It doesn't matter whether that word sat is in the third position or in the first position, because our attention weight just is based upon similarity, an inner product. And these indexes here, n and n dash, they don't tell us position. All they do is tell us which words we're using. The denominator here is just a number, it's a constant, so that doesn't depend upon position. So what we've actually got here is attention weights that have no information or no knowledge of the positions of the individual words, where they sit in that sentence, which means they can't actually be very good at doing their job. Okay, somehow we've got to be able to introduce positional information into the whole process. Somehow we need to be able to distinguish the fact that this word the at the end of the sentence or the end of the prompt is different to the beginning, the first the in the prompt at the beginning of the sentence. Somehow we need to separate them, we need to introduce some information that distinguishes between these two instances of the word the. And there's a very easy way we can do that. We can just create some new position-dependent vectors and combine them with our original starting embedding vectors. So what we do is we've got our individual starting vectors. We've got their positions in the prompt. Here I've represented that by the symbol I. And all I'm going to do is create some new vectors that only depend upon the position. So I take the position, the value of the variable I feed it into a very simple function p, and I'm going to explain what that function, an example of that function is in a moment. And that gives me these orange vectors. Each of these orange vectors will be different to each other because we're feeding in different values of I. And all I do is I take these orange vectors and I numerically combine them together. I just literally add them to my starting vectors. So for example, at position 1, I take my first word, which is the, I combine it with the output from this function p, where I've input the value of I equals 1, and I combine them and I get this green vector here. So this green vector represents the word the at the first position, and I just do the same for all the other words in my prompt. By the time I've got to the end, here I'm starting with the same vector for the word the, but I will be combining it with a different vector because I'm inputting I equals 5 into my function p. So I will actually get a slightly different green vector to when I was looking at the first instance of the word the. So this introduces a difference between the two instances of the word the, and through the training process, the model can then exploit those differences to work out how to use that to actually take into account the positional information of the different words. So what do our functions, what does that function p look like? It can be very simple. In the original attention is all you need paper, which is the paper from Google and MIT, which really sort of kick-started the whole LLM process about 10 years ago. They used very simple functions. They just used sine and cosine functions. More modern LLMs tend to use more sophisticated positional encoding functions. And in fact, those positional encoding vectors can also be part of they can just be model parameters that the training process learns. I'm not going to go into the details of some of those more sophisticated functions, other than to say what their purpose is to distinguish the different positions in our embedding vectors. So, finally, and I promise no more lies, that is true. Our transformer looks like this. We take word embedding vectors, vectors that represent each word. We combine them with vectors that represent the positions. And when I say combine, literally, we're just adding them numerically. We feed them through a sequence of transformer blocks, and we get a series of updated vectors which are context aware. These are vectors that take into account the preceding context, the preceding part of the prompt. And that's literally how a transformer works. So again, I will emphasize, rather than thinking of transformers and LLMs as being these horrible, scary things, all they're doing is taking vectors, they're going through a process of calculating weighted averages to give you new vectors that you can feed into a bog standard machine learning model to predict the next word. Whew, we covered an awful lot, so it's time to wrap up. What did we actually learn? Well, we learned that actually next token prediction is a very powerful capability. Yes, I focus solely on predicting the next word in a sentence, but what I want to get across to you is that is just an example of predicting the next token in a sequence of tokens, and being able to predict the next token in a sequence is actually a very powerful capability, particularly when those tokens become things like actions and decisions. You can actually start to get into agentic systems. To solve our actual problem of next word prediction, we had to solve a couple of problems. First of all, we had to map our large vocabularies down into much smaller dimensional vectors. You may think of 300 dimensional vectors or 8,000 dimensional vectors as being very large, but compared to the starting vocabulary size, actually these are very small. These are essentially small vectors. But most importantly, we were able to transform each of those vectors into new embedding vectors that were context aware. They were aware of what other words were around them. And that's the thing that gave us the capability to predict the next word in a sentence. The downside to that is these models had an awful lot of parameters. We had to learn, I just kept on saying, we have to learn these parameters via a training process. We can do that because we have an awful lot of training data available. We have data from the internet. We also have a lot of compute power available to us using, obviously advanced NVIDIA chips and various cloud computing, platforms. We can also train these models if you've got a lot of money. Okay, that's probably part of the operative thing here. You are able to do this training process if you've got a lot of venture capital behind you. So I'm not saying it's easy. In fact, there's a huge amount of things that I just skipped over in this talk because I was trying to give you a very quick introduction to transformers and large language models. So there were lots of things I didn't cover. So for example, how you can actually improve the prompt by things, how you can make a prompt very specific to your particular domain or your particular data set or your particular area of expertise. So things like retrieval augmented generation, where you might take an information store to actually improve the prompt, how you can break the prompt down into a series of steps. So things like chain of thought allow you to improve the prompt so it can actually do checks on itself and actually use the output from one prediction to actually improve the prompt for the next stage in its overall process. You can also use things like, you can take some of these large models and actually tune them to your own particular domain, your own particular data set, by doing things like updating the parameters using things like low rank adaptation. These are all things on really more on the engineering side and actually on the usage side. So that's why I haven't gone into them. Also in the restrictions of time, I can only go into the sort of like the high level mathematical concepts. So with that, I'm going to say thank you very much for listening. I will take questions. Again, if you want to know anything more about me, you can either go to my LinkedIn page, or if you want to go to my blog post, my blog site, you can do that as well. As I say, thank you for listening. Quite happy to take questions. Stunned you into silence. Go on.
What is the main difference from mathematical side between different models? It's more advanced.
Yeah, it's the bigger difference is actually probably occur in the application domain. Well, it depends. Sorry, it depends what you meant by different models. If you meant different companies, probably not. Well, maybe not a great deal. It's more if you're using a transformer, say, for doing something like essentially extending a sentence versus maybe doing something like translation between different languages. So the kinds of things I was explaining, in these slides are what is known as decoder-only models. You also have encoder models, and you have encoder blocks and decoder blocks, and you can combine those together to do things like translation between different languages. So there, the architecture changes slightly. But inside even an encoder block, it's still the same idea. You're creating new context-aware embedding vectors. It's just how you use them. Things like multimodal systems, where you're using both text inputs and maybe audio input as well, visual inputs as well. The mathematics changes in terms of you've got different architectures. Fundamentally, the ideas are the same. You're always representing your inputs via some sort of vector in maybe a smaller dimension, a lower dimensional space, and transforming those vectors.
What is the motivation to start from linear simplification?
You mean why all those linear transformations? Well, you saw how complex.
You go to linear.
Well, okay.
Next, simplify to linear. Okay.
Yeah, okay. I would say, well, look how complicated it was just with those linear transformations. And the main non-linearities occurred in two places. One, to convert inner products, scalar products, which is linear algebra, to convert those into probabilities. There we were forced to. When building the classifier, we had another softmax function. So when you want to calculate probabilities aren't linearly extensive. They don't continually increase in size. So probabilities by definition are non-linear. So we have to have a non-linear model there. Anywhere where we could get away with simplifying, with a simple linear transformation, we did. And even then, we have a horrible model, well, I'd say horrible system, a complicated system that has billions of parameters. Introducing further nonlinearities would make it even more difficult. So we only had nonlinearities where it was necessary, or in that bit where we wanted to combine the rows, where we wanted to mix up the features in a single vector, and we introduced the neural network. So we stick to linear transformations because, well, it's simple, and we keep things simple, particularly on an engineering side. Yeah, it's complex enough just with those linear transformations, let alone before we, yeah. Yeah.
I understand you also use cosine proximity.
Yeah. Yeah.
Is that more like geometry of the whole embedded vector to be pointing?
Okay, so cosine. So when we're calculating the similarity measure to feed into our attention weights, that's essentially cosine similarity. Because if you think about cosine similarity, it's just the inner product divided by the normalized length of the length of the individual vectors that you're getting. Typically, we will work with normalized unit length embedding vectors. So actually, inner product here is the same as cosine similarity. The reason I didn't talk about cosine similarity is it's complicated enough just saying inner product before then introducing another function, cosine as well.
These new ideas for similarity are very different than cosine similarity.
Sorry?
You mentioned that in different models, yes,
Yeah.
you go with different similarity measure, more advanced than cosine similarity. What are these ideas?
Okay, so the place where we have much more complex is in the where we can. I'm not quite sure. So what you're referring to. So we make that. So in the positional embedding vectors, we might use a more complicated functions than sine and cosines here. For the actual, so I'm just going to go back. For the actual attention weights, no, we're always just calculating an inner product between a query vector and a key vector, and we just feed that into a softmax function.
Always.
Yeah, always. I mean, that's complex enough. It also does the job. You know what it's need to.
Yeah. The process you've described sounds very neutral and very objective, but we know the outputs of the chatbots is non-deterministic and bias can be introduced. Is that another level entirely above what you've described?
Well, it depends. So one thing I haven't gone on to is in a longer version of this talk, I actually go into essentially why you can get things like hallucinations. So when we're actually producing the making the predictions of the next word, we're essentially using a probability distribution. In this case, I'm going to make I use the most probable word as my prediction. Sometimes we also use we might sample from this probability distribution. So most of the time, if I were to draw a sample from this probability distribution, I would get the word mat. Occasionally, I might get the word sat, even though it's got low probability. So occasionally, when you use LLMs in a sampling process, you've all probably played around with that temperature parameter in an LLM. That determines the degree of sort of how concentrated the probability distribution is. That's when you can start to get some weird outputs. You can also get weird outputs when your model of this probability distribution is very, very wrong. That really depends upon how well you've constructed the prior context, which is why things like retrieval augmented generation help reduce that by adding in more relevant information into the prompt. When you're talking about bias, that's very much dependent upon things such as the training data. A lot of that comes down to how well you construct that training data. It comes down to the sort of ethical, processes you've got around your whole engineering process, and that's very much, requires skilled human oversight.
So to predict the next word, actually, you allocate probabilities to any possible word.
Yeah. So if you had a vocabulary of 50,000, this probability distribution wouldn't have. Here I've got 5 bars. It would have 50,000 bars. So to go back, what you might not have realized is these vectors here, which is where which I use to create the probability distribution. There's 50,000 of these vectors. These models are huge in the number of parameters.
Very good, well done, and it's really good talk. And you talk here about context, and the context you talk about is within the actual sentence.
Yeah.
But then, if I'm Dr. Seuss, the answer to this is completely different to if I'm not Dr. Seuss, for example. You know, so because then the context becomes, oh, the user is different.
Yeah.
It might be a different context again if the weather is different. So if I say, what should I do tonight? Well, depending on where I am, what the weather. How do we train now to add these extra layers of context of user-defined and news-defined that would provide a better answer?
Okay, I'm not quite sure I follow. I'm going to give an answer, but I think I might be slightly misunderstanding you. What I was trying to get about in answer to one of the earlier questions is the quality of the information you put into the context is highly critical. So if you put much more relevant information, so you're going to get a better output. But now you've actually got sort of modern sort of LLMs, which allow you to have huge context windows. You can put an awful lot of information. So I'm not sure whether this is what you meant, but essentially you can put that information into your prompt, which is why when people sort of try and train people in how to prompt, they say put as much relevant structured information, the output to be much more relevant and much more useful. So rather than saying things like give me a recommendation of what to eat tonight, you say, right, I'm a vegetarian, I like these kinds of foods, I ate this last night, what I'm looking for is something like this, and you're going to get a much more focused, useful answer out. I don't know if that's quite what you're referring to. So you could put some of that patient information, that patient context as well into your prompt.
So, I mean, you've answered it by saying just put more in the words.
Yeah.
So essentially, and I think I don't disagree. I'm just wondering, because obviously if I just go to someone random in the street and ask them, hey, what should I eat tonight? They'll look at me and they'll assume things just based on who I am, depending, So I don't know what the right answer is, but it definitely is a question that is going to be generated more and more to give a better answer than just, okay, I've told you this, so therefore this.
Yeah, so there is a skill in prompting and how to craft a good prompt, but it really ultimately comes down to make the prompt more, condition your prompt, or make the information on which you're conditioning you're wanting to condition the output relevant to the thing, as relevant as possible to the thing you're trying to predict. You can do that through just a good prompt, which is something you gain through experience. You can also do it via these, things like retrieval augmented generation, where you're also using a separate knowledge base to actually refine your prompt and help you make it more relevant. There are other things.
Yes, just whilst you're thinking, it might be interesting one day when I put into Claude, hey, what should I respond to my mother? And it responds saying, you really should not talk to your mother anymore. That would be an interesting one.
Yeah, possibly if there's other. I mean, you can actually help. Obviously, you can have system information stored about you. So you might type that in and think, how did it know that? It's because you've already given it information in a previous sort of. You're feeding into the same session and it's got information about you already.
Yeah.
Thank you. Very clearly showed us how it works.
Yeah.
Why does it win out over previous approaches like RNN or LSTM? Why did OpenAI go with a transformer? Why could they not go off of those?
Yeah. Okay. That's a. It's not okay. I like to, as I said, I gave this talk as a previous longer bootcamp tutorial. I'm trying to get back to, and the bit I took out is when I was showing you this naive approach. The example I used to actually demonstrate the naive approach was actually a first-order Markov process, what I used to use. And what I tried to show there was if you have a system where you're just conditioning just solely on the previous word, you're going to get a rubbish system out. And it's because the thing you're conditioning on is actually very limited information. So the thing about transformers is they are trying to very efficiently do this process of how can I distill the information in the prompt down into a single vector. And essentially they're doing that very efficiently. other systems such as recurrent neural networks, LTSMs, you've got some similar ideas there, but they're not doing it as efficiently, which means they're not actually able to take into account such a long context window into account as well. And so you get some, you'll see the forgetting process happen a bit more obviously in, say, something like a recurrent neural network. If you had a problem where you only needed to take into account a short amount of context, maybe sort of 5 or 6 tokens back, there's probably actually going to be very little difference in performance. It's when you're actually getting into the longer context that you'll start to notice the difference. My personal opinion is because they're doing that process of how do you distill that context as efficiently as possibly down into sort of a very small amount, a small amount of information, a small representation that still actually contains a lot of the information. And that process of self-attention, that weighted averaging, is extremely efficient in doing that. Don't know if that quite answers your question. Yeah, go on.
So you gave an example earlier that ChatGPT 4.5 stills the vocabulary down to 3,000 dimensional.
Yeah, I can't remember.
Space. So then you apply transformers to make your prompt context aware. Or,
yeah.
Is that the same vector space, or is it a different vector space? So is it as if it's finding a unique coordinate in that space that represents the whole prompt, or is it a different vector space?
No, so, well, okay. So what you're doing is you're starting with a word, like you say, a word, yeah. You're starting with a point in this space. You transform that vector represented by that dot into a new vector. So you're still in the same space. The difficulty might be is like, okay, can I interpret that new point as representing a word? And the answer is no, essentially no. So whilst you're in the same space, you're not necessarily representing a word. You've got a representation of the word, but it also of your starting token, but it's also taking into account the preceding context information. So if you think about these points here, each of these dots is a word. If I were to take one of these dots and say, transform it using some random transformation, there's no guarantee I'm going to end up on one of these other dots. Yeah, and so although I'm staying in the same space, I haven't got necessarily got another word.
But it's like inventing its own word.
Yeah, well, it's representing its own numeric representation of something. In this case, we know what it's representing because we constructed it. It's coming up with a representation of that word plus all the preceding words with the appropriate with the appropriate weighting, the appropriate combination for solving the task that I'm actually wanting to solve, because I've trained all the parameters to tune the attention weights in the appropriate way.
But if you gave it a dictionary definition, it might get close.
It might do.
The word that you looked up.
I mean, again, one of the code examples. So in this tutorial session, a longer one I run, I actually go through an example where I take these word2vec embedding vectors, and I just have a bit of fun. You might have seen the when word2vec originally came out, they gave an example of things like how you can take the words king and queen and man and woman and construct them. So what's the difference between a king and a man? Well, it's essentially just one's a monarch, the other's just a member of the sort of an ordinary pleb. And if you say if you take those two vectors and subtract man from king, that tells you the difference between sort of an ordinary member of the public and a monarch. If you apply that difference then to say woman, you find out actually the closest vector to it, the closest word is queen. Okay, so I actually also do a fun bit, which is take a random word. The word I use is rain because it's Manchester, and I just apply a random linear transformation to it. I just rotate it randomly in this space, and I go, right, what does this new vector represent? Does it represent a word? And obviously it doesn't. And actually the fun part is seeing what word did it end up closest to. And believe me, you can have some real fun. You take the word rain, randomly rotate it in this 300-dimensional space. I think it ended up with some meat dish that I was completely, some bizarre sort of Mongolian meat dish I've never heard of before. And it's like, how did I get from rain to this Mongolian meat dish?
So you refer back to the earlier talk, which is a longer version.
Yeah.
Is it worth trying to chase that up? Is that available?
The recording is, but it's behind a paywall. But the slides and the code examples are in my GitHub repository, so you can probably get those.
Okay. You showed a slide with multiple transformer layers.
Yeah.
How do the model designers arrive at a set number of layers? And how big are those layers compared to other layers?
Right. Okay. As in, is there some process of optimizing this? I don't know. Now I suspect what it is they add as many as they can possibly get away with, and the training process still be, first of all, A, stable, because it takes an awful, there is some instability, can be some instabilities to these training process. B, have they got the money to actually train it? And basically, when you're seeing, these new releases of models, often in the early days, often what the differences between the different releases of the models was just adding extra transformer layers to it. It was literally just increasing. The first one, I think, ChatGPT, whatever it was, that came out in about 2022, the first one, I think it had eight layers. So we're talking of order 8 layers. I don't know what they're up to now, but I wouldn't suspect it's actually that many before. Most of the advances have occurred in sort of other areas in the architecture. As in, I don't think anybody's going to try and train a model which has got, say, 1,000 transformer blocks, because it's just like, well, yeah, diminishing returns. Yeah. Sorry, at the very back.
How does what you described relate to the mixture of experts?
It did. Yeah.
Sorry, what was the question?
How does what I've explained, as in this bit, as in the multiple transformer blocks, relate to mixture of experts? It doesn't really, or not in a way that I would think of it. So I'm going to duck that question and say it doesn't, and not explain any further. Yeah, sorry. Yeah. Right. Yeah. Okay. I deliberately skipped agentic, referring to agentic AI. Other than that bit where I was trying to convince you that being able to predict the next token can lead to agentic capabilities. Right. Where do I need to go to? I want to go to. Oh yeah, here. Okay, my classifier. Okay. Right. What I really skipped over is, in the examples I was showing you, where we actually are using an LLM to predict the next word, we are essentially, we're creating these context-aware embedding vectors, and then we use them to actually train a multi-class classifier. In this case, this is my classifier here. So what we're actually doing is we're rewarding the loss function we put is on the actual discrepancy between when we're training our multi-class classifier, the loss function we use is the cross entropy. It's just the loss we suffer we make in, if I predict a word and I get it wrong. When you're coming on to more agentic systems, we're still using things like next token prediction, but actually we also include a reinforcement learning stage in here as well. So we actually put the reward, the loss function, essentially on the actual reward. Essentially, is the reward that we put on completing the task successfully. So we've got the usual Bellman equations that follow on from this. So although we're predicting the next word, the thing we minimize is not the accuracy of how well that next word or next token is predicted. It's how well the actual task is completed. So that's what allows us to actually do, create agentic systems. Now, what you're asking is, okay, that's how you might predict next action, but how do we actually couple next action to actually some sort of tool execution? That starts to get us into the engineering side of things as well. And again, that's out of my expertise, so I'm going to duck that one as well. But certainly to do agentic, we actually need to do more than just next word prediction. We also have to have this extra reinforcement learning stage on beyond this as well. We put the loss function. We started to introduce rewards, and we put our loss function essentially on the reward.
Okay, so then you combine both loss functions.
Yeah, well, we wouldn't even have a loss function for the next token prediction. It would just, we would literally just predict the next token or the next, in this case, next decision, and then beyond that, the next decision and next decision, and then we would just measure its performance just like we would in any other reinforcement learning system, and train it that way through, and updating the policy using the Bellman equations.
I was wondering if it was like Copilot or Gemini, there's something, in tools like Copilot or Gemini, there's something called as deep thinking, where you just wait a bit longer to get a better output.
Yeah.
So by switching to that version, are you essentially just switching to a model based on a higher dimensionality, or are there other ways in which the model can be made?
No, okay, there may be things like, in the deep thinking, you're actually introducing more things like chain of thought steps into it. So it's where it's also checking its reasoning process. A lot of those details are hidden how precisely it does. So I'm not really able to comment other than sort of really speculating about what it does.
Yeah. Is it possible to synthetically construct a series of transformer weights to get like a very predictable operation? Like, can you do like arithmetic or something by feeding in an accurate way?
You could do, but there's probably easier ways of doing it. I mean,
I'm just wondering about the limits we know about correctness.
Yeah, I mean, probably the easiest way to do, create weights, tension weights for doing arithmetic would actually just create a large data set of arithmetic examples and then train, which is what we do. Yeah. I mean, could I manually construct them in a sort of forward process? It would be very difficult to do, and I suspect you wouldn't be able to do it much through more than one sort of attention head, not even the multi-headed attention. And ultimately you'd probably give up and say, well, I'll just train it on a load of numerical arithmetic examples of arithmetic.
Let's thought maybe provide some insights into what's
Yeah.
going on.
I mean, if your goal was to predict, create some system that could actually verify that could be verified for its accuracy, formal accuracy for implementing arithmetic calculations, there are much better architectures to use than a transformer to do that.
Oh, for sure.
So, yeah.
I've noticed when using ChatGPT, there's been a couple of times where it'll randomly insert a word in another language, and I've seen other people have this problem, and they've suggested that it's because, for example, if you had this cat sat on the mat, it would just put an Arabic word for mat instead of an English word.
Yeah.
And it would be because the probability scores are similar in both languages, but then surely it's not. You don't normally get Arabic words in the middle of an English sentence, so why does it do that? And does it not have any concept of different languages, like human languages?
Yeah, no, it does. I suspect there's something to do with what was in the training data that's allowed it to do that, and so it's managed. It has found some examples. The training data has included either multiple languages, or actually there was some instances of sort of text which contained both languages in it. So. I'm just sort of guessing there, but that's why by construction these things don't have an intrinsic knowledge, an intrinsic understanding of different languages inside them.
Does the natural language capability model, because they talk to you in a very convincing way?
Yeah.
Is that an emergent property from next word prediction, or is that some other training?
No, it's literally next word prediction. But remember, in most systems you're using, this context window is extremely long. So they learn how to actually construct appropriate next words based upon a lot of information in the preceding sentence. And if you continue that process, so you make a prediction of the next word, and then you make the prediction of the next word, you've still got a lot of that original context, that original prompt that you input. So you can actually extend an initial prompt quite a long way before it's actually starting to solely have to use it using its own predictions. If you provide a long prompt, you will get what sounds like quite an intelligent answer coming out, and it's all coming out from essentially next word, or next token prediction. People say, well, are these things intelligent? What I like to comment is, on the observation I make is, I think what it tells me is actually how much of human interaction and how much of human conversations is just our fast system one processes kicking in, and we're not actually thinking very much about what's coming out of our words. I'm talking to you now, I'm doing a bit of processing, but I'm having to think on the spot fast. So actually I'm not dwelling on my actual thought processes. And yet, we have conversations with each other, we sound intelligent. I think what you're going to actually find is a lot of what we thought was our unique intelligence is actually just essentially this next word prediction. Yeah.
Is that related just to how you train, or is there some
No, there's different mathematics in there. Again, it's not something I've gone into here. It's I haven't got it's an extra talk in itself, and again, it's not my actual area of expertise. So, but it's yeah.
It's more of an engineering.
Not necessarily. There are some mathematical details to it, from what I understand. But it's it's extra tricks that you can play. But it does. I mean that inference time compute actually gets very expensive. So. It's a nice trick. Well, that's more than a trick. It's a powerful extension to the capabilities, but it can actually get very expensive. It sort of significantly increases the costs of using. The major providers, I think, found that they were hitting a lot of issues with the cost of actually providing these systems because of that inference time compute. Yeah.
In the world, and then there's like 170,000 English words,
mm-hmm.
and that has been reduced to 300 dimensional. So I want to know, is it more words means more dimensions, or all the language in the world has to apply the same rules?
No.
Why it has to be 300?
It doesn't. Okay. So what you want this to do? Remember, we're starting with a very we've got a very large vocabulary. If we were to represent each word just using that what we call one-hot encoding system, that's actually a very inefficient way of representing the words, because we're using one dimension per word. Whereas if I start with a 300-dimensional space, I've still got a very large space. So by mapping down into that 300-dimensional space, I can still capture a lot of the semantics, the rich structure about what the words represent. Yes, there will be some loss of information. By definition, you're going from vectors in a 170,000 dimensional space into points into a 300-dimensional space. So you're going to suffer some loss of information. But you're probably not going to suffer that much loss, because a 300-dimensional space has still got an awful lot of room in it. The more the bigger the vocabulary you've got, perhaps then the more concentrated, the more crowded it gets, and that's why you might use a higher dimensionality for doing that mapping. But actually, there's probably very little trade-off from actually going to really big dimensionalities, which is why you'll see on something like ChatGPT 4.5. Actually, they're still only talking about a 3,000 dimensional embeddings, because there's probably very little actually to be gained between going from 3,000 to 8,000. No one's suddenly going to use 50,000 dimensional embedding vectors. So what you actually want to really take into account is, okay, what are the sort of different semantic relationships and concepts that I've got available, that are present in that language? So imagine I'd used a very low dimensionality, like a dimensionality of say 20. I would be compressing all those 170,000 words into a 20-dimensional space. They would get quite crowded. I would have words which were technically very unrelated, possibly ending up close to each other. So I wouldn't actually have very much semantic separation. So I would struggle to distinguish concepts. So I want my dimensionality probably to be large enough that I'm getting some separation of concepts, but actually that doesn't take that higher dimension to actually do that. But yes, if I had a language which had many more, a much higher vocabulary size, then I would need a higher dimensionality to probably map down to. Also, if I had a language where there were lots of very different semantic concepts that I needed to be well separated, I might also go for a higher dimensionality.
Would you say the statistical prediction for natural languages is harder than a programming language? Stricter syntax?
Yes and no, but possibly well, it depends on whether you think there are more semantic concepts that get created from the combination of those. Yeah, I agree with the point about you've got a smaller syntax, you've got a smaller set of atoms operators. Do you have a richer set of possible combinations that think of all the programs that get created? compared to the sort of, you might say that, text, but certain languages, the output from human language tends to follow very, sort of well-defined genres, and actually maybe the genres aren't. I don't know. This is not my area, but maybe they're not as rich as we think they might be. Maybe the output from a programming language is maybe a bit more. It makes more wider use of the vocabulary they've got, and so it might be there. Per vocabulary, per word, per token, there's a more semantic variation in a programming language. I don't know. Short answer is I don't know. And I don't actually know what dimensionality people use for mapping. I've never thought about it before, so it's interesting. I'm going to go away and look it up now. Yeah, sorry, at the back again.
So different models use different dimensionality.
Yeah.
At the start, which then you apply transformer blocks.
Yeah.
Map into a different vector space. How do they decide which ones to use, which dimensions to use in the first place?
Again, I think that there's going to be a bit of trial and error there. Literally, I mean, you're probably going to use more than 300 because 300 was what Word2Vec used, and that was about 14 years old. Also, the sort of training data sets are larger. So Word2Vec, I mean, for example, this data set here was trained on about, I think it was 1 million Wikipedia articles. No, so I think it's a million, yeah, it might be 1 million Wikipedia articles or something like that. Whereas the training data sets you're using in a modern LLM will be a lot bigger. So they probably actually wanted to sort of make sure that they were distinguishing the concepts, the concepts that are the topics that are available, that are present in those training data sets. They wanted to make sure they were well separated. So you clearly want to go bigger than 300. I think it was a bit of trial and error. They probably first of all tried 1,000, then 2,000, 3,000. They played around with it a bit. Maybe they wanted. Maybe some of this might be just differentiating yourself from your competitors. But I suspect this is largely a bit of engineering trial and error in terms of they will also have versions of this where they tried 9,000 dimensionality and had to go and saw how well how accurate the actual holdout accuracy was.
Can I use what other people have tried and then improve on it? So can I use 2,000 dimensions and
You could do so. If you could get hold of these embedding vectors, then you could. You could use them in another application. Yeah. I mean, could you improve upon them? I'd sort of like go, well, why would you want? In what way would you want to improve upon them? I mean,
rather than start from scratch and figure it out.
Could you fine tune them? In other words, could you take them and take another data set and?
Fine tune so long I use 8,000 dimensions. If I want to train improved model, can I use that as a start?
Yeah. So you could. I mean, you could take these these embedding vectors, and you could use them as the basis of your own model. So if you think about it, when you do things like fine tuning on an LLM, typically the bits you're fine tuning are actually those transformation matrices, those matrices that I referred to. Here and here. So the actual bit we update is typically not the actual embedding vectors. It's not that part when we're fine tuning an LLM. It's actually other parts. So yes, you could, but most of your it's actually easier to fine tune these bits using things like low rank adaptation. It's so these are the parts of the way you'd actually focus your fine tuning effort. But you could do fine tune the embedding vectors if you really wanted to.
From scratch, it would be very expensive.
Yeah.
Yeah, I think firstly to the point. So my training budget for cloud compute was $400,000 a month. So just be careful before you start hammering loads of training into systems. It can get very expensive. Is end of sentence, and maybe this points out to you getting up, is end of sentence just another word? Or because when does an LLM shut up?
Yeah. Okay. So get there.
What does finally mean?
Yeah, this end of sentence was just a token. So actually, it's just an extra token in my vocabulary. So I should have actually technically put this end of sentence also in this probability distribution here. I just didn't because I didn't want to confuse you at that point. So yes, when it hits end of sentence, that's an instruction to the actual computer to say, stop running this iterative process.
Okay, many thanks indeed. I think David's done a fantastic job. Excellent presentation. Huge amount of questions and answers. Been on your feet for more than an hour, so it's absolutely excellent. Can you join with me in thanking David again? In conclusion, I just wanted to remind everybody that the details, Christina's ready to put them up on Meetup. The next meeting is on the 21st of July, and it's Stuart Coulson, and his topic is, if I were a betting man, then a statistical society would agree about AI. Be very interesting to hear what Stuart's got to say, but it will be another excellent lecture. Many thanks again to David. This has been fantastic. Thank you very much indeed. Wish you all safe travel. Thanks. Okay.
Yeah, a bit hot under the lights.
Excellent.
Yeah, I was a bit worried when I asked the questions and everyone went blank, and then